I would like to give this talk in English. So it's always frustrating to give a talk in this large audience, especially after having left in time for a couple of years without giving any talk in the KS meeting. But he had asked me to do a talk to my presentation.
Okay, so I will start with, this is about the gravitational waves, in particular mostly gravitational wave activities in Korea. And so I'll start with this picture. I found this picture when I was trying to clean up my office before the retirement. And I was surprised that I still have this picture, which was taken in 2000 in Potsdam. So I was invited to give a talk in this third LISA symposium, and I didn't know anything about gravitational waves except that I used some keywords of gravitational waves in some of my papers. That's maybe why they invited me. And I still remember this meeting very well, although the audience was not very impressed by my talk. I was impressed by other talks. And also I found that there are many important persons, including two Nobel laureates, Gibson and Rainer Weiss. Gibson is here, Rainer Weiss is here. Unfortunately, this person was supposed to get the Nobel Prize, but he passed away just before the Nobel Prize was announced. Anyway, so this meeting gave me a motivation to start gravitational waves, in particular together with the people in Korea, not myself. So I organized a group called Gravitational Wave Group, and we had a kind of kickoff meeting in 2003. Unfortunately, I don't have any photos at that meeting. And then we had studied by ourselves to understand what the gravitational waves are and how we participate in worldwide activities in the gravitational wave research. And then for that, actually KISTI, Supercomputer Center at KISTI, provided a big support. I didn't put it, but also we have been supported by Asian Pacific Center for Theoretical Physics in Pohang. And after several years of work or studies, we were finally admitted to LIGO Scientific Collaboration in 2010. And we began also working on CAGRA from 2011. Recently, I'm not in part of this, but many Korean members are also working for Einstein telescope, which is a third generation gravitational detector to be constructed in Europe. Although the site has not been decided, the approximate timeline is about late 2030. So Korea, although the share is small, Korea is a member of this consortium and led by Sung-ho Lee at KASI and Chung-Lee Kim at Ewha Women's University. So if anybody is interested in joining this, please contact these people. Then in 2021, I was fortunate enough to get the research fund from the National Research Foundation, and this is called Center for the Gravitational Wave Universe. And this program is called National Science Challenge Initiative Program. The duration is from 2021 July until the end of 2025. And it's basically gravitational wave research. So we are working on theoretical studies of gravitational waves, but another very important keyword is electromagnetic counterpart. So for that, we are constructing a wide field spectroscopic facility for rapid identification of gravitational wave sources, and I'm going to mention about this later. So my topic will cover includes a short summary of LIGO-Virgo-Colour observations and bright siren measurement, which is a multi-messenger astronomy, and the facility, serendipity, and prospects of dark sirens, etc. So this shows the gravitational wave spectrum, like electromagnetic spectrum, starting from ranging from gamma ray to radio. Here also the very low frequency is 10 to the minus 16 hertz, which is actually the period corresponds to the age of the universe. And then you have higher and higher frequencies, and current detectors are operating at a frequency range around from 30 to a few thousand hertz. So this last part is the only accessible frequency range from the ground. But I'd like to also talk about something we can achieve by slightly shifting this toward the low frequency. This is the current status of the gravitational wave observations. We have been doing these observations from 2015. The first observing run is called O1, and O2 and O3. We finished the O3, we are in the middle of fourth observing run. And in the first observing run, there is a first detection of gravitational wave in 2015, although it was announced in early 2016. Then in 2017, we had the detection of the multi-messenger gravitational wave, which means that both gravitational wave and electromagnetic wave were detected. In the first observing run, we are here. We have finished the first part of the fourth observing run, and this marks the first line of our optical facility in late 2023. We are in the late part of 2024, so you can see we are in this part. And these numbers correspond to the horizon distance for kind of standard the gravitational wave source, which is the binary neutron stars. So at the beginning it was 80 megaparsec. Now we are around 160 megaparsec, which means that the horizon distance has been doubled. And the doubling horizon distance means that we expect at least order of magnitude more frequent detection. This is some of the highlights from the fourth observing run, which started last year, and this must be wrong. About 150 detections so far from this year alone, from about 1 year. And most of them are binary black holes, and we have some exceptions like neutron star black hole binary and some other cases, etc. So the comparison between O3 and O4 is nicely shown here. That this is the accumulated number of detections from the start of the observations. So this slope corresponds to the sensitivity. So the third observing run has relatively low slope, and fourth has slightly higher slope. And that also means that we can see the sources at further distances in the fourth observing run, which is shown as a red dot compared to the green. Okay, so what can I do with the observations of gravitational waves? From the beginning, actually, LIGO was people call it a detector, but actually its name, if you look at the name, it's an observatory, which means that they are aiming to make routine observations. And from the observations, we want to learn some physical parameters about the sources, and this is how we obtain physical parameters. So this is what we observe. These are the signals, the intrinsic signals, and these are projections. So detectors gravitational waves have two polarization. They are projected to a single detector. So any detector has this this function, which is called the strain amplitude. And for the case of circular binaries, about 15 parameters are imprinted on the waveforms. Among the 15, 8 are intrinsic parameters, which means that the masses and spin, etc. And there are 7 extrinsic parameters like location in the sky, distance, and the relative configuration of the orbit, time of the merger, phase, etc. So these are already a huge number of parameters. But if you ignore spin, the number of parameters reduces to 9, still not so small number. And the duration of the observation from frequency until merger can be expressed by this simple formula. So the one thing I would like to emphasize is that this has a very steep dependence on the frequency, which means that if you start observing the gravitational wave from 1 Hertz, it takes some time, but if you start from 0.1 Hertz, it may take more than 1,000 times longer. One of the parameters we are interested in is the distances, and we can measure the distances to the object without any calibration, etc. Just because the shape of the gravitational waves actually show the parameters, intrinsic parameters like masses and so on are imprinted, and the amplitude is dependent on the distance. So you first determine the physical parameters from the shape alone, then you compare the amplitude from some kind of standard distance amplitude, you can get the distance. However, it has a very strong dependence on the orbital inclination, iota, which is the inclination angle between the line of sight and the orbit. So these parameters, these ones are we derive, but actually it has cosine iota term, and therefore you have a significant uncertainty in distance estimation. Otherwise, everything can be determined without any help. So this one shows the first estimation of the distances and then corresponding Hubble constant from the measurement of the gravitational wave 170817, which was located about 40 megaparsec away. And as I said, the distance itself has a large error, and therefore the estimated Hubble constant has a large wide distribution. And these two lines are so-called the Hubble tension, where the red one comes from Planck observations, and green one comes from the Hughes observations, and they don't match each other within the error. But this one opens a possibility of using gravitational waves for the probe of the universe in various ways. So if you have a lot of such events, you can decrease the width of the error, and therefore you can get a more precise value. And if you can apply this kind of technique to the even further distances, you can see the acceleration or deceleration of the universe. Okay, let me turn to the 7-dimensional telescope for rapid follow-up observations. And there have been a few special sessions about this telescope system, and therefore many of you already know. But this is basically composed of 20 telescopes of 50 centimeter aperture that corresponds to effective diameter of 2.2 meter. And each telescope has 2 medium band filters. So if you combine all these telescopes and observe the same object together, then you can get the spectrum ranging from near, it's not really ultraviolet, but the short to long wavelengths. And because these telescopes are small and wide fielded, you can cover large area of sky very efficiently, and you can observe over and over to get the time series. And therefore it's suitable for the survey of transients such as gamma ray burst, kilonova, and also other surveys require large field of view and spectroscopic information. Currently 16 telescopes are installed and it's already being used for the observation. And it's located in Chile. And this one shows the power of this telescope system. So if you find some transient, you want to know the nature, but from the wide band observations, you cannot distinguish between this type of source and the other type of source which has a lot of spectral features. But if you have medium band spectroscopic data, you can sample this one very densely, and therefore you can easily distinguish. So that's the one of the very important power of this telescope system. Now, if the gravitational wave is coming from the merger of 2 neutron stars, they naturally produce electromagnetic radiation. But as we have seen, most of the sources we have detected so far are black hole binaries, and they generally don't emit any electromagnetic radiation. So, furthermore, even binary neutron stars, if they are very far, you cannot actually detect the electromagnetic counterpart because the kilonova are not very bright sources. So the gravitational wave sources which don't have any electromagnetic counterpart is called dark silent, which means that you have the detection, you know the distance, but you know where it's coming from. Now, the reason why I'm saying that you know where it's coming from is that the identification of the host galaxy is extremely difficult. But of course, you can still use dark silence to constrain, for example, cosmological parameters and statistically. And I'm going to talk about some possibility of identifying these host galaxies with future detectors. But that has to have a coverage of low frequency. Now I will show you why we can detect the gravitational wave sources, the counterpart with the low frequency detector. So this is a continuation of the difficulties of identifying host galaxies. We have now the localization of the source in the sky is done through the triangulation, which means that if you have several detectors, the arrival times are slightly different. And using this information, you can constrain the location in the sky. And that was done even for the gamma ray astronomy in early days. So this is called triangulation. So accuracy of triangulation increases with the number of detectors and of course with other things. But for example, signal to noise ratio. If they are strong, you have a better localization. So these diagrams show actually the fraction, the cumulative distribution of localization as a function of square degree for large number of gravitational wave detectors. So you can see that in this LHVJIAC, and each letter corresponds to a gravitational wave detector. So among these, I think that there are 7, but out of 7, 5 are actually planned, constructed, under construction or being planned. Now the final AC is these 2 detectors are not even planned. It's just under the imagination of some of the astronomers. And I was associated with people who were trying to construct some gravitational wave detectors in Australia and China, and that's why we have added these 2 detectors. And you see that the 90% credible region in terms of square degrees is increasing. Increasing means the worse localization with the distance of the source. The reason is that as the distance of sources become larger, you will have lower signal to noise ratio. So, for example, as a typical number, black hole binaries at 400 megaparsec can be localized within 0.1 scale, 20% of them. Even 0.1 scale, there are about 10 to 20 galaxies. So that illustrates how difficult it is to localize. Now the situation will become different with the advance of new detectors. So this is the diagram showing the sensitivity of the current detector, LIGO, and the green is the Einstein telescope I just discussed, and CE is a cosmic explorer to be constructed in the US. And this Voyager is something in between. So we are now living in this detector, with this detector. And the horizon distance as a function of the mass is shown here. So for the LIGO, it's relatively close because BNS mass is about 3 solar mass, total mass, and in terms of redshift is less than 0.1. But if you go to the future detectors like Einstein telescope and the Cosmic Explorer, you can reach redshift of 3 or even 10. So that illustrates how powerful of the future detectors. And even this improvement of sensitivity gives you an improvement of signal to noise ratio that can be imprinted on the accuracy of the localization. But if you have a detector, this is the detector frequency, sensitivity, and various detectors. So this is a ground-based detector, and this is advanced LIGO, and the low curve is the Einstein telescope. But if you have something in between, this is LISA. This is LISA, which gave me the motivation to work on the gravitational waves. But LISA will be flying in late 2030s, and in between there is even no no form project. But people proposed a few detectors in this range, and it turned out that this is called mid-band range. And mid-band detectors are extremely useful, actually, for something like cosmological applications and so on. The reason is that this is a sensitivity curve. Again, I'm amplifying only this part, and so the 10 to minus 2 Hertz, 0.1 Hertz, 1 Hertz, and 10 Hertz. So the ground-based detectors are sensitive from about 30 Hertz. But there are some proposals which can be sensitive in this wavelength, in this frequency range. If you consider the mass combination, which is it's a typical, or this is a first detection actually between two black holes around the 30 solar mass, and if you can start from this frequency 0.07 or something like that, actually the gravitational wave signal stays in the band for about 60 days. And if you go to slightly higher frequency, it stays short. Up to now, most of the gravitational wave detection, the gravitational wave stays in the band only within a second or just few seconds. For the binary neutron stars, they stay for a couple of minutes, but that's all we have. But if the gravitational wave signal can be observed for a long time, then we have big advantages, like the modulation of the signal due to the relative periodic Doppler shift because of the Earth's rotation or orbital rotation because they are space-based detectors, and also the long-term variation because of the orbit around the sun. And if you take these into account, actually the localization angle and distance can be significantly improved. Now, how much improved is significant? So we want to localize these sources within a volume where you expect only 1 or 2 galaxies. Then you can identify the host galaxy. That can happen if with the low frequency detectors. This is the simulation I had with the postdoc, and it shows the localization volume 99%. So very highly likely you can localize within this, like this is 10 to minus 2 cubic megaparsec. This is 10 to 4 cubic megaparsec. So the number of galaxies per cubic megaparsec, it depends on the luminosity cut of the galaxies, but it's something like within 0.01, something like that. So if you can localize the volume, occupation volume within 100 megaparsec, then you may claim that this is the only galaxy that can host the gravitational wave source. And then you can use this kind of information to construct the Hubble diagram. So you measure the redshift because you know which galaxy has this gravitational wave source, and then luminosity distance. And this is the blue, green is the neutron stars, and the violet is the black holes. So you can sample quite you can draw Hubble diagram for relatively wide range of distances. So that's the possibility, and then you can, for example, if you are interested in the Hubble tension, you can measure the Hubble constant, and you see the progressive narrowing of this probability density with the number of such identified sources. And if the binaries have eccentricity, they have more features in the gravitational waveforms, which means that you can determine the distances and this sky location even better. And this is the is how much gain you can get. So 0 is the no gain, and 10 to the minus 2 is 100 times better localization. This is just in the sky location. But if you have eccentricities, large eccentricities, you will have a significant gain. Okay, so, but the question is whether these binaries really have eccentricities or not. However, there is some concern when you find eccentric binaries, because any determination of the parameters require accurate knowledge about the gravitational waveforms. Now, I'm talking about the gravitational wave observations lasting for days and weeks, even almost a year. If you have some source that lasts 1 year, you have the big advantage because you have full sampling of the orbit around the sun. But during this 1 year period, these binaries emit huge number of signals, huge number of cycles, and you have to have a really very accurate waveforms. This one is the extreme case where suppose you have the gravitational wave source whose eccentricity is 0.001. It's very close to the circular orbit. But if you analyze the data assuming circular orbit, then you will have a shift in this parameter. This is the mass, and mass is directly related to the distance. And therefore, you can see that this is a systematic error. So the width of this curve corresponds to the statistical error, but the distance between the peaks are the systematic error. Of course, the absolute value of this systematic error is small, but you still have some systematics. You have some biases in your distance estimation if you don't use the correct waveforms. So that's something we have to do, and don't worry about early young people, because there are lots of things you should do before we have this kind of sciences. So this is one example we have done with the eccentric waveforms. This is post-Newtonian calculations, and you can see that red and blue are different post-Newtonian order, and they don't match each other. They are approximately the same, but they don't match each other perfectly, which means that you still have a room to improve. Another thing is that the eccentricity, we don't even understand what the eccentricity is. So the eccentricity is uniquely defined in Keplerian orbit, but in relativistic orbit, actually some of these eccentricities are dependent on the choice of the coordinate, and therefore it's not clear when you talk about eccentricity what kind of quantity you are talking about. So that's something you have to sort out. This one illustrates that this is actually a kind of measurement of eccentricity in a coordinate independent way. So it's a bit complicated expression, but we can define some eccentricity. But even if we have done so, we saw that there is some mismatch of the waveforms depending on different waveform models. So you can define the eccentricity the same way, and there are several different approaches of obtaining the waveform, and if you compare these waveforms, actually sometimes they don't match each other. So also, this one actually illustrates nicely about this. So this is TEOB and CEOB. They are different waveform models, and different waveform models. We have defined the eccentricity in the same way, but they don't match each other. So this is something we have to understand. Okay, so I tried to finish it in time, and I think I have achieved almost. So to summarize, this is a very obvious statement. Identification of the host galaxies is very important for the astrophysical and cosmological applications. And obvious way is to follow up observations in electromagnetic radiation, but they are very rare. So, so maybe in the future we have to rely on the increasing the accuracy of the sky localization and distances, so that we can identify the host galaxy uniquely. Although not everything, but at least for some dry sources. Okay, so just as I emphasized, we need accurate waveform models for long duration of binary orbit evolution in order to fully utilize the capability of low frequency detectors. Thank you very much.
질문을 받을 수 있는 충분한 시간을 두고 맞춰주셔서 정말 감사합니다. 우리 이영모 회원님께 질문이나 코멘트 있으시면 말씀해 주십시오. 예.
한번 질문드려요. 세븐지티 텔레스코프를 가지고서 지금 현재까지 트랜지언트라든지 어떤 특별한 현상을 관측한 경우의 예를 좀 알려주실 수 있는지, 그 다음에 두 번째는 이 풀스백의 그 부분만 사용을 하나, 아니면 다른 데서 코드를 받아서 하는 경우인지.
예, 제가 그냥 간단하게 답변을 드리고 우리 임명신 교수님이 그걸 담당하고 계시니까 좀 더 자세하게 말씀드리도록 하겠습니다. 우선 뭐 실제로 she asked me if there was any real observations of the transient with 7DT, and the answer is yes, because they have been always keeping eye on the alert from the gravitational wave detectors as well as others like gamma ray burst and so on. So there have been a lot of observations. As for the gravitational waves, there has not been any counterpart yet, although there have been some possible sources. And and that's the first part. And second part, this will be used for many other purposes, because the transient observation, the transient happens only very rarely, like once every few days, once every week, or something like that. So other than these times, you can use the 7DT for other purposes, and they have 7 programs. So, Professor Milsini.
네, 그냥 한국말 할까요? 네, 그러니까 지금 중력파 사건 같은 경우에는 이제 괜찮아 보이는 사건을 여러 개 관측을 했고요. 근데 실제로 EM 카운터파트가 있을 만한 사건은 없었어요, 지금까지. 그렇지만 이제 바이너리 블랙홀 같은 경우에도 로컬 시뮬레이가 좋은 경우에는 그 관측을 통해서 이제 호스 갤럭시가 될 만한 은하들을 시프트에다가 결정할 수 있기 때문에 좀 유용하다고 싶고 관측을 해왔고요. 그 외에도 이제 슈퍼노바라든가 감마레이 볼스 같은 것도 좀 관측을 해서 성능이 어떻게 되나라는 것도 살펴봤습니다. 그리고 이제 다른 또 그 사이언스를 하시는 분, 그러니까 뭐 오픈 콜은 지금 없지만 그 다른 주변에 있는 분들께 이제 한번 사용하시라고 이제 인터뷰를 해가지고 여러 이제 관측 프로그램을 돌렸고요. 여전히 이제 그런 관심 있는 분은 이제 또 약간 이동을 하지만 그 관측 시간을 갖다가 이제 메인 서베이 말고도 이제 할 수 있게 좀 할 예정으로 있고, 포스터가 하나 있는데요. 7DT 가지고 예를 들면 영스텔라 오브젝트를 갖다가 관측을 하고 이제 그 영스텔라 오브젝트의 스펙트럼 모양이 바뀌는 모습을
예, 박명우 의원님.
질문이 두 가지인데 하나 받고 또 하나 더 생각하겠습니다. 우선 그 마이켈슨 인터프로메트리 방식이 아닌 방식으로 지금 만들려고 하는 어떤 계획들 중에 구체화된 것들이 있는지. 예, 그 가장 뭐 많이 구체화되고 있는 게 그 역시 인터프로메트리긴 한데 이거는 저 레이저를 쓰는 게 아니고 매터 웨이브를 사용한 게 있습니다. 그 매터 웨이브는 매터 상태를 아마 그게 이제 보존 상태로 만들어야 될 텐데요. 그 스핀 같은 적당히 골라갖고 그래갖고 거기에다 레이저를 쏴갖고 얘네들이 이제 모멘텀 이런 것들을 측정해서 하는 건데 이제 그 지금 미국에도 그 컨셉을 추구하고 있는데 스탠포드하고 또 어디 딴 데가 있는 걸로 알고 있고 그다음에 중국에도 그걸 하고 있고 파리에서도 하고 있고요. 그다음에 이제 뭐 국내에서는 그 슈퍼컨덕터를 이용해서 이제 하는 거를 프로포즈를 하고 있는데 아마 그거는 지금 당장 디텍터라기보다는 프로토타입을 만드는 데 좀 집중해야 될 거라고 이제 생각을 하고 있습니다. 예.
두 번째 질문은 이제 바이너리 블랙홀이 저렇게 많이 발견되는데 아스트로피직스 쪽에서 저 바이너리 블랙홀들이 어떻게 생겼는가에 대한 컨센서스 같은 게 조금 만들어지고 있나요? 아니면
뭐 컨센서스라기보다는 생각보다 그 과거에는 사실 바이너리 블랙홀을 만드는 채널보다 그냥 소위 아이솔레이트 에볼루션을 다들 선호했었거든요. 그게 무슨 뜻인가 하면은 그냥 바이너리가 나중에 진화를 바이너리 상태로 가는 거. 그 다음에 또 하나의 그 제한된 거로는 이제 다이내미컬 바이너리라고 해서 그 사실 제가 다이내미컬 바이너리 때문에 이걸 여기 이제 불려가게 됐는데 그거는 사람들이 뭐 선호하는 사람도 있고 선호하지 않는 사람도 있고 그렇습니다만은 역시 그래도 뭐 관심은 갖고 있는 그런 채널이었었어요. 그런데 실제로 관측을 해보니까 이런 다이나미컬한 프로세스를 만들어져야 설명할 수 있는 것들이 몇 가지가 있어요. 그건 어떻게 하는 거냐면 이 스핀 엑시스를 어느 정도 추정을 할 수가 있는데 사실 스핀 엑시스는 정확하게 못하더라도 이게 얼라인드 돼 있는지 안티 얼라인드 돼 있는지 정도를 하거든요. 근데 안티 얼라인드 돼 있는 경우가 꽤 있다는 거죠. 그 반반씩은 아니에요. 반반씩. 근데 이 다이나미컬 프로세스는 반반씩을 만들어냅니다. 근데 이제 그걸로 봐서 다이나미컬 프로세스 분명히 존재하고 거기에 아이솔레이트 메커니즘이 존재하고 근데 어느 게 어느 걸 오염시켰는지 잘 모르겠어요. 근데 저는 사실 그게 굉장히 내가 그 다이나미컬 프로세스를 연구를 했지만 나도 그게 머저리티가 될 거라고 생각은 안 하고 있었거든요. 근데 생각보다는 꽤 많을 것 같다는 느낌이 들어요. 뭐 많으면 30-40%까지 가능하지 않을까.
절대적인 개수도 30-40%까지는 된다고 생각합니다.
그렇게 될 수 있을 거라는 거죠. 현재 저 스핀 디스트리뷰션을 보면은 그건 뭐 굉장히 극단적이죠.
전체 퍼센트로 보는 건 그렇게 될 수 있을 것 같아요. 절대적으로 그만한 수를 만들 만큼 무거운 그렇게 갈 수 있는 시스템들이 있는가 하는 것은
있죠. 충분히 있죠. 구상선단이 많으니까.
옛날에 그렇게 이야기 안 하셨잖아요.
옛날에도 나는 딴 사람은 몇 개 만들지 모르지만은 제가 얘기했던 건 딴 사람 몇 개 만들지 모르지만은 구상선단에서 만들어지는 것만 해도 2015년 관측하면 바로 관측될 거다 그랬죠. 근데 진짜 바로 관측돼서 뭐 어떤 잘못된 이유로 제대로 된 예측을 하는 경우도 많잖아요.
예, 이상승 회원님.
네, 감사합니다. 중력파 연구가 처음 이제 검출되고 나서 굉장히 센세이션했고 기대를 많이 먹었고 또 역시 멀티 메신저 어스트로노미로 이어진다고 해서 기대를 많이 했습니다. 근데 이제 EHT도 이제 처음 발견 이후에 어떤 사이언스나 어떤 새로운 뉴 피지스를 더 주도할 수 있느냐 이런 기대가 있을 것 같은데, 예를 들어 EHT 같은 경우는 블랙홀의 섀도우와 재생 커넥션 연구로 이어지고, 새로운 프로젝트가 이제 블랙홀 스피를 정확히 제작 이렇게 이어지고 있는데, 중력파에서는 말씀하신 그런 사이언스들 중에 좀 이제 발견 이후에 좀 더 저희가 기대를 많이 볼 수 있는 어떤 피직스 같은 이런 부분들이 어떤 게 있는지, 이게 구체적으로 또 블랙홀 스피를 정확히 측정할 수 있는 그런 기회도 될지.
그 스핀을 측정할 수 있으면 좋은데, 이 대개 블랙홀, 스텔라 매스 블랙홀의 스핀이 좀 약한 것 같습니다. 적어도 그 정도는 좀 알고 있는데, 그게 그 약한 건 뭐 상관없지만 약하다는 것은 측정하기가 어렵다는 얘기죠. 그런 문제가 있고, 또 하나는 이제 뭐 그 자기 연구 분야에 따라서 이게 좀 다 다른데, 그 스텔라 에볼루션 하는 사람들은 매스갭에 굉장히 관심이 있습니다. 매스갭이라는 게 두 군데가 있는데요. 뉴트론 스타 매스하고 그 다음에 텐솔라 매스, 그 사이에는 블랙홀이 없을 거다 하는 그 로우 매스갭이고요. 그 다음에 이제 70 솔라 매스를 넘어서면은 소위 페어 인스테빌리티 때문에 그 블랙홀을 형성하지 않고 별을 약간 통째로 그냥 날려버리는 그러기 때문에 70 솔라 매스 이상은 존재하지 않을 거다 하는 그런 매스. 그 70 솔라 매스 하면 그 다음에 매스 어퍼는 뭐냐? 그 다음은 뭐 전혀 다른 얘기가 다른 메커니즘. 어쨌든 그 두 가지가 있는데, 지금은 아까 제가 설명을 자세히 안 하고 넘어간 그 하이라이트 중에 로어 매스갭에 있는 경우가 하나 있었고요. 그 다음에 어퍼 매스갭을 넘어간 것들은 꽤 여러 개 있습니다. 그래서 그 스텔라 에볼루션 하는 사람에 따라서 이제 얼마나 그걸 시리어스하게 생각하느냐는 좀 사람마다 좀 다르죠. 어떤 사람은 뭐 그거 파라미터 좀 조정하면 된다는 사람도 있고, 어떤 사람은 그건 뭐 완전히 새로운 개념을 도입해야 된다 이렇게 주장하는 사람도 있고, 제가 그렇게 봤는데, 아무튼 그거는 뭐 그게 중요한지 안 중요한지 잘 모르겠지만 어쨌든 그런 것들이 있고, 그 다음에 이제 매스 펑션을 구하는 게 있는데, 저는 그 매스 펑션에 대해서는 사실 약간은 뭐라 그럴까, 그렇게 큰 정보를 주지 않을 수도 있을 거라고 생각했는데, 사람들이 꽤 시리어스한 게 이렇게 픽들이 몇 개 있는데, 그 이론적으로 예측하는 픽하고 좀 비슷해요. 그 다음에 이제 저는 개인적으로는 인터미디에이트 매스 블랙홀이 그 다음 단계일 거라고 생각합니다. 그래서 인터미디에이트 매스 블랙홀을 발견하기 위해서라도 우리가 좀 로우 프리퀀시를 좀 푸시를 해야 돼, 더 작은. 근데 그게 왜 힘든 건가 하면, 이 지상 위에서는 소위 그 사이스믹 모션 때문에 소위 사이스믹 웨이브가 있죠. 그 웨이브가 계속해서 중력장의 플럭츄에이션을 만들어냅니다. 그게 이제 뉴토니안 노이즈라고 하는 건데, 그 뉴토니안 노이즈는 액셀러레이션으로 보면 컨스턴트예요. 근데 그걸 이런 스트레인으로 환산하면 그걸 2번 시간에 더 미분해야 되거든요. 그럼 F-2승이 거기 들어가요. 그러니까 로우 프리퀀시를 가면 거의 절벽처럼 그 관측을 못하게 하는 그런 영향을 줍니다. 그래서 그것 때문에 지상에서는 이제 저주파를 하기가 어려운데, 뭐 저희가 지상을 약간 좀 푸시해 보려고 하는 게 슈퍼컨덕팅 디텍터였었고, 그렇지 않으면 진짜 그 피하는 방법은 스페이스로 가는 거죠. 그래서 스페이스에 올라가서 아까 저는 이 리사보다는 진짜 사이언스가 위치한 게 여기라고 생각합니다. 여기 노란색, 파란색은 약간 애매해요. 그 매시 블랙, 슈퍼 매시 블랙홀도 아니고, 그런데 요 사이에는 인터미디에이트 매스 블랙홀도 할 수 있고, 그 다음에 우리 스텔라 매스 블랙홀을 굉장히 오랫동안 관측할 수도 있고, 그래서 할 수 있는 게 굉장히 많습니다. 여기는 PTA, 펄사 타이밍이라고 해요. 이거 좀 다른 스토리죠.
네, 시간이 충분히 경과했기 때문에 질의응답을 여기서 마치겠습니다. 그럼 대한민국 학술대회로 선출되신 이정모 의원을 다시 한번 축하드리면서 훌륭한 강의를 해주신 대한민국의 박수를 부탁드리겠습니다. 감사합니다.